Hi everyone, this is Kiranmai from H&S department. Today we are going to have a session on dielectric properties of materials. In that we are going to discuss about the basic terms regarding the dielectric properties. Those are electric field intensity, electric flux density, electric dipole, dipole moment, polarization, polarization vector, polarizability, dielectric constant, susceptibility, displacement vector, and some of the relations between the above different properties. First of all, what is electric? What is a dielectric material? Dielectric materials are the materials which does not contain free electrons, or the number of such electrons is too low to constitute electric current. So we can indirectly call dielectric materials as insulating materials. But insulating materials are used to resist the flow of current, whereas dielectrics are used to store the electrical energy. This was the main difference between the insulating material and a dielectric material. Insulators are not conductors of electricity, but a dielectric is a component which can store electrical energy. So dielectrics are the non-metallic materials of high specific resistance and have negative temperature coefficient of resistance. These are the different points regarding key points regarding a dielectric material. So comparable to the conductors, dielectrics are insulators, does not conduct electricity. Charge given to them remains localized, and for a particular field strength, they lose their insulating character. These are the four different characteristics of a dielectric material comparable to a conducting material. Then what is electric field intensity? Field intensity is nothing but the force acting per unit test charge when it is placed in a electric field. The force acting on a unit test charge when the test charge is placed in a unit electric field, then it is called as electric field intensity. And from Coulomb's law, you know that force between any two charges Q1 and Q2 is given by 1 by 4 pi epsilon naught Q1 Q2 by R square. Then F by Q1 is nothing but 1 by 4 pi epsilon naught Q by R square. So that F by Q, force per unit charge, is nothing but electric field intensity. Therefore, E is equal to F by Q is equal to 1 by 4 pi epsilon naught Q by R square. Now, in this, if you place epsilon naught aside, you will have 4 pi R square, which is nothing but surface area of a sphere. So you, in place of 4 pi r square, you can replace it with A. Therefore, Q by epsilon A is nothing but electric field intensity. And the units for electric field intensity is, as it is the ratio of force per charge. So units for force is Newton and units for charge is Coulomb. Therefore, units for electric field intensity is Newton per Coulomb. Next, electric flux density. So electric flux density is nothing but the number of flux lines passing per unit surface area of a given material, which is represented with a letter phi by A. Electric flux is represented with a letter phi, and phi flux per unit area is nothing but electric flux density, and the units for it is Weber per square meters. Then coming to the electric dipole, this electric dipole is nothing but an arrangement of two equal and opposite charges. Here the two equal and opposite charges means they are equal in magnitude but opposite in charge. Those two charges are arranged at certain distance. Then the arrangement is called as electric dipole. The product of this the product of this charge with the length between them, distance between them, is nothing but electric dipole moment and is represented with a letter small p. P is equal to charge of the dipole into distance between the poles, q into 2l. Since it is a product of charge and length, the units will be coulomb meter. Coulomb meter. So coming to the next point, that is polarization. Polarization is the phenomena. It is actually a phenomena which will happen when a dielectric material is placed in external field. So when a dielectric material is placed in external field, what happens? The positive depending on the field direction, positive and negative charges will get displaced in opposite direction. Such a phenomena is called as polarization. Due to application of electric field on a dielectric material, the positive and negative charges of the material get displaced in opposite direction and get situated on the surface of the material. Such a displacement due to application of external field is called as polarization. Then how to calculate how much polarization is happened in the material? For that, it is defined with respect to polarization vector. which is a ratio of dipole moment per unit volume. Ratio of dipole moment per unit volume. So as it is represented with a letter capital P, P is equal to dipole moment small p by volume V. So uh, the units for this one will be coulomb per square meter. Coulomb per square meter. So it is also defined as ratio of induced charge per unit area. How suppose like dipole moment is nothing but q into 2l, and volume you can write it as area into 2l. So q into 2l by area into 2l, 2l will cancel out. So q by a, which is defined as the ratio of induced charge per unit area. Induced charge per unit area. Due to application of external field, charges will get displaced, so that internal induced field will be produced. Due to that induced field, how much charge is produced? That induced charge per unit area is nothing but polarization vector. Then coming to polarizability, polarizability is defined as the like if you increase the field strength, automatically dipole moment also increases, because the number of charges getting polarized also increases with the field strength. Therefore dipole moment also increases with the electric field intensity. Therefore dipole moment is proportional to electric field intensity. If you remove proportionality, you have to place one constant. Dipole moment is equal to alpha into E, where alpha is called as polarizability. So just rearranging the terms, then alpha is equal to P by E. We can define polarizability as ratio of dipole moment per unit electric field. Dipole moment per unit electric field, whose units are coulomb square meter per Newton. Then dielectric constant or relative permittivity. It is defined as the ratio of permittivity of medium to permittivity of free space. Epsilon r is the relative permittivity, that is equal to epsilon by epsilon naught. Since both the denominator and numerator are same terms, there is no units for relative permittivity. And relative permittivity is otherwise called as dielectric constant, which can be defined in terms of capacitance, where it is defined as the ratio of capacitance in medium to capacitance without medium, that is K is equal to C by C naught. Then coming to the susceptibility, again to define susceptibility, let us consider one dielectric material on which an electric field is E is applied. So if you increase the field strength, dipole moment increases. If dipole moment increases, polarization also increases. Therefore, polarization is directly proportional to applied field intensity. So P is equal to Xi E, where Xi is a proportionality constant called as susceptibility. Xi is equal to P by E, where it is defined as susceptibility is defined as polarization vector per unit electric field. Polarization vector per unit electric field. Then coming to the last definition, that is displacement vector, which is defined as the ratio of charge per unit area, and whose units are coulomb per square meter square. Both polarization vector and displacement vector has same units, and the formula is same, that is charge per unit area. But displacement vector is due to the applied electric field, whereas polarization vector is due to the induced electric field. So coming to the relation between displacement vector, polarization vector, and electric field intensity, uh, let us first derive a relation between displacement vector and electric field intensity. That is, D is equal to Q by A, charge per unit area. Just multiply and divide with epsilon on both on the right hand side of the equation. Then Q by epsilon A into epsilon, where Q by epsilon A is nothing but electric field intensity. Therefore, D is equal to E into epsilon, which is called as relation between displacement vector to electric field intensity. And as we know that the formula for the permittivity in terms of relative permittivity, epsilon is equal to epsilon naught into epsilon r. Just substituting it, you'll get a relation. D is equal to epsilon naught epsilon r E. The second relation between displacement vector, polarization vector, and electric field intensity. To derive it, let us consider one parallel plate capacitor in between which a dielectric material has been placed. Now let us apply an electric field EA to this parallel plate capacitor so that left side plate will become positively ionized, a positive plate, and right side one will become negative plate. Due to application of electric field from left to right, there will be an induced field on the surface of the uh, dielectric material, which is acting just opposite to the applied electric field. Therefore, the total field across the plates of the capacitor can be given as E is equal to summation of applied field and induced field, EA plus minus E bar. The here minus represents that EA and E bar are in reverse directions. So EA is nothing but applied field, that is Q by epsilon naught A, minus E bar is nothing but induced field, that's what induced charge by epsilon naught A. Now if you take epsilon naught as a common, take it onto the other side, you will get epsilon naught A is equal to Q by A minus Q prime by A. Charge per unit area is nothing but displacement vector. Induced charge per unit area is nothing but polarization vector. So substituting them and rearranging, you will get D is equal to P plus epsilon naught A. This is the relation between displacement vector, polarization vector, and electric field intensity. The last relation between polarization vector and electric field intensity is, so from the above two relations, we had D is equal to epsilon naught E, and D is equal to epsilon naught E plus P. So just combining these two, equating these two, you'll get P is equal to epsilon naught minus 1 into epsilon naught E. This is the relation between polarization vector to electric field intensity. There is one more relation which is derived in between susceptibility and permittivity, that is given by from the above relation P is equal to epsilon r minus 1 into epsilon naught E, and from the definition P is equal to xi. Now if you just compare these two equations, the coefficient for electric field intensity is epsilon r minus 1 into epsilon naught in one equation and xi in other equation. So just comparing those two equations, xi is equal to epsilon r minus 1 into epsilon naught, which is a relation between susceptibility and permittivity. Thank you.